All right, let's begin. Today we're talking about the second fundamental theorem of calculus and some of its applications. Well, really, applications of the general fundamental theorem of calculus. Okay, so first we're going to pick up where we left off yesterday with an example that illustrates what the second fundamental theorem is all about. So, a few reminders. Homework's due Monday night. You have everything you need to be able to do it. And then quiz due tonight. Make sure you get it done. Yeah, those are my any questions on those announcements? All right. Well, last time we left off here, we want to find the integral from -3 to x of 3t squared, 3t cubed minus 4t squared with respect to t. All right. So the integral from from -3 to x. All right. So what does the fundamental theorem, the first fundamental theorem of calculus, say that we need to do? We need to find an antiderivative of this, right? All right, so I'm going to break this up into the integral from -3 to x of 3t cubed plus the integral, or dt, plus the integral from -3 to x of -4t squared dt. I'll say 95% of the time you want to break up the integral into its pieces when you're doing a sum. Then this is equal to 3 times the integral from -3 to x of just t cubed dt minus 4 times the integral from -3 to x of t squared dt. What is an antiderivative of t to the third?
T squared over 3.
T, I'd be careful. We have t to the 3, so to integrate this, find an antiderivative, we add 1, right? Yeah, we're going to add 1, and we're going to get t to the 4 over 4. So I'm going to get 3 times t to the 4 over 4. So that's that power rule for integration, right? And then minus 4 times, well, what's an antiderivative of t squared? T cubed over 3. Very good. T cubed over 3. And now I'm going to evaluate this at t equals x and subtract off when t is equal to -3. Okay, so any questions so far? All right, when I plug in t equals x, not a lot changes here. It's just I get an x instead of a t, right? So this is going to become, well, I gave myself 0 room. This is going to become, go away, go away. There we go. This is going to become 3 times x to the 4th divided by 4 minus 4 times x cubed over 3. And then minus, when I plug in -3, so 3 times -3 to the 4th divided by 4 minus 4 times -3 cubed over 3. Any questions on this so far? So notice this is a function of x. This is a constant. We can work out what that constant is. I'm not really concerned about that with this example. notice the second part of this question was, what is the derivative of your answer with respect to x? Okay, so let's take a derivative then. This is technically your answer. You can find out what this constant is. But once you do, when we differentiate what we have, the constant is going to go away, right? So when I take the derivative of this thing, what do I get? Well, what's the derivative of 3x to the 4th over 4? Yeah, 12x to the 3rd, and that over 4 is still down there, right? And then minus, what's the derivative of 4x cubed divided by 3? 12x squared divided by 3. And then really minus, the rest of this doesn't have an x in it, so I can say minus 0, right? So the derivative of this thing that I got when I integrated is this. And when I simplify, well, 12 over 4, that's 3. So I get 3x cubed minus 12 over 3, that's 4. So 3x cubed minus 4x squared. And notice that this is the exact same thing that we started with as far as integration goes, which makes sense because, again, differentiation and integration are opposite processes. So if I differentiate something that I integrated, hopefully I end up back at the same place. Now, it's not perfect because when you integrate something that you differentiate, you have to add that plus c, right? So they're not like fully opposite processes. But going this way, it does work exactly like we want. So if you differentiate something that you integrate, you get back exactly what was under the integral sign. And that is entirely what the second fundamental theorem of calculus says. Okay, so the second fundamental theorem of calculus has to do with taking derivatives of functions that are defined by integrals. The first fundamental theorem is about integrating things that are derivatives, right? Second fundamental theorem is integrating things that are, differentiating things that are integrals. Okay, so let's look at another example. As an example, let's look at this function here, capital F of x is equal to the integral from -1 to x of t squared dt. Okay, so this is a function of x, right? Because I can plug in any old x into here and get an output. What is f of -1? What's the integral from -1 to -1 of t squared? Zero. Yeah, very good. It's 0, right? If I integrate, this is that idea of if I just integrate a function over a single point, well, the area of the line is just 0, right? Cool. Then what is f of, say, I don't know, +1? Or at least how would I find it? Well, I would just integrate. We're not going to actually do this integration, but to find f of +1, you integrate from -1 to 1 of t squared. And in general, you can find any x value you plug in, you can find that integral, right? So this is a well-defined function of x. Okay, and the idea is, given any x, well, this function tells me the area underneath the curve t squared from from -1 to x. So just think of this function as you can slide this x around and it will tell you the area underneath there. When I first saw a function defined by an integral, I was very confused. Okay, so if anyone ever feels confused about this, just let me know. All right, so for this function, we can calculate what I believe, we can calculate exactly what f of x needs to be, though. We can actually perform this integration, right? Because the integral of t squared, or an antiderivative of t squared, well, using that power rule, we get t cubed over 3. You add 1 to the exponent, and then you divide by your new exponent, okay? It's the exact opposite of the power rule for differentiation. Okay, and so when you calculate f of x, what it actually comes out to be, you get x cubed plus 1 over 3 when you actually carry out that integration. Okay. So then, well, we can take a derivative of capital F of x, and what do we get when we do that? Well, this is just x cubed over 3 plus 1/3. So when I take a derivative with respect to x of x cubed over 3, what do I get? Just x squared. When I take the derivative of 1/3 with respect to x, well, 1/3 is just a constant, right? So that's going to give me x squared plus 0, and so I'm just left with x squared. Okay. Questions on this process? So the x squared, again, that's exactly what we started off integrating. I mean, we started off integrating t squared. The variable doesn't really matter. We got the function, the original function that we integrated, we got that back. And so this is what the second fundamental theorem of calculus says is always going to happen. When I take a derivative of a function that's defined by an integral like this, I'm always going to get this sort of cancellation. Okay, so here is the second fundamental theorem of calculus. If little f is a continuous function on an open interval I containing the point A, then for every x in that interval I, the derivative with respect to x of the integral from A to x of f of t with respect to t is just equal to f of x. Okay, so the first fundamental theorem tells me what happens when I take an integral from A to B of a derivative with respect to x, right? I just end up with f of b minus f of a from the first fundamental theorem. The second fundamental theorem tells me what happens when I take a derivative of an integral. It swaps the integration with the differentiation, okay? And it looks a little different because you need to have, f of x, because you have that variable x as a bound of integration, but I mean, that's not a big deal. Okay, so this is the second fundamental theorem. It tells you what happens when the order is swapped. All right, and then a proof, quote unquote, of the second fundamental theorem. Technically, we need to look at the limit. If I define capital F of x to be this integral from a to x of f of t dt, well, technically, to show that this is a differentiable function of x, we need to show that the limit as h approaches 0 of f of x plus h minus f of x divided by h, that limit exists. Okay. That's not too hard to do. I'm going to show you a different, not technically rigorous proof, but it's one that helps me remember what's really happening. So we want to look at what is the derivative of the integral from a to x of f of t with respect to t. Right? Well, let's pretend that I know an antiderivative of little f. Okay? Let's say capital F of t is an antiderivative of little f of t. What does that mean? Who can tell me what that means again? What was it? Yeah, little f of t is the original, and so if big f of t is an antiderivative of little f of t, then what does that actually mean? What is?
Means you can
What was it?
you can differentiate big F of t and get f of like
Exactly.
little
The
f of t.
derivative of big f of t is little f of t. Exactly. Okay, so that's what that means. Now, in assuming that we can find this antiderivative, I'm assuming a lot. Okay, so this is where this breaks down a little bit. But let's pretend that it's easy to find the antiderivative, or let's assume that little f of t has an antiderivative on the interval I. Okay, that's a big assumption. Well, then the integral, if we can find that antiderivative, then the integral from a to x of little f of t by the fundamental theorem, the first fundamental theorem of calculus, is equal to what? Not just x minus a, but big f of x minus big f of a, right? We take an antiderivative of the thing we're integrating, and we evaluate at the endpoints and subtract, right? So if we can find an antiderivative of little f, then the integral defining this function is really just this. But now, if I take the derivative of both sides, which is what we originally wanted to do, let me give myself a little room. Well, the left-hand side is what we were trying to find to begin with. What do I get on the right? Well, I get the derivative with respect to x of big F minus the derivative with respect to x of big F of A. What's the derivative with respect to x of big F of x? Remember, big F is an antiderivative of, yeah, we're going to get little f of x. Very good. So this is equal to little f of x. What's the derivative with respect to x of f of a? Remember, a here is just some number, some fixed number in the interval. So big F of A, it's not little f of A. Ooh, you said a correct word in there. No, you're fine. So I'm evaluating some function at A, right? A is some number. Does it depend on x? Is there any x happening in there for the derivative with respect to x of f of A? So there's no x's happening. So what happens when I take a derivative of something? Yeah, 0, right? Minus 0. And so we just get f of x. And that's what we wanted to show, right? That the derivative with respect to x from a to x of f of t dt is f of x. So again, in assuming that little f has an antiderivative on this interval, that's a very big assumption. So this isn't a technically, again, rigorous proof. This wouldn't hold up in your later real analysis course, but it holds up just fine for us. It gets the idea across. Okay, so any questions on this? All right, well, let's use this then. Find the integral, or sorry, the derivative of the integral from 0 to x of e to the minus t squared over 2 with respect to t. Okay. So this is an example of a function where you can't really find its antiderivative. It exists in a higher realm of functions that we can't just write down easily. So it does have an antiderivative, but we can't find it very, very easily. Okay, so the derivative with respect to x from 0, the integral from 0 to x of e to the minus t squared over 2 dt. What is the second fundamental theorem, which I write as SF, second fundamental theorem of calculus, tells us that this is equal to what? Well, let's pretend for a second that we know, let's pretend that we know some antiderivative of e to the minus t squared over 2. So that means capital F prime of t equals e to the minus t squared over 2. Let's pretend we know that that exists and we can write it down. Well, then the integral on the inside, the integral from 0 to x of e to the minus t squared over 2 dt. Well, if I'm assuming big F is an antiderivative of e to the minus t squared over 2. So what is this equal to in terms of big F? So I can't actually evaluate if I later, so next week we're going to learn about what's called a U substitution. And this squared is throwing that off. Normally, if it was just the integral of e to the t dt, then yes, then it would just be e to the t. But this function, we can try all day long to actually write down an antiderivative. That's going to be a fruitless endeavor. Okay. So the idea is, well, I'll just pretend that I know the antiderivative. I'm calling it big F. I don't actually know what it is, but I'll write down big F is that antiderivative. So then what is the integral here just in terms of big F, some antiderivative of the thing inside? What does the first fundamental theorem tell us?
Would it be f of x minus big F of x minus f of a, or 0 in this case?
Good. Yeah, first fundamental theorem tells us find any antiderivative of the thing on the inside, then the integral is that antiderivative evaluated at the endpoints and take a difference, right? So now we want to, normally we getting to here, we would say, well, that doesn't get me anywhere. I still don't know big F. But we don't really want to know big F. We want to know the derivative of this thing, right? It's going to give me e to the, well, let me write this out. This is the derivative of f of x with respect to x, right? So that's f prime of x. What is f prime of x, big F prime of x?
F of x, little f of x.
Little f, yeah, and little f was this guy, right? So we're going to get e to the negative x squared divided by 2. And that's our answer. we are done. Any questions on that? So this function on the inside here is actually used a lot in probability if you multiply it by a constant. And it looks like the bell curve, right? If you look at a graph of this thing, e to the negative negative, I'll just do x squared divided by 2. So this is just the usual bell curve. Again, if you multiply it by 1 over the square root of 2 pi. But really, what we're trying to do with that integral, the integral tells me what's the area between x equals 0 and x equal and any old x. So so if x was 1, then it would just be what's the area from 0 to 1 under this curve. By taking the derivative, we're finding how that area changes when we change x a little bit, right? So that's the whole idea. Cool stuff, cool stuff. All right, let's look at a tougher example. Let's find the derivative with respect to x of the integral from -5 to x squared of sine of t with respect to t. All right, so first off, I maybe should have I'm going to change this. I'm calling it audible. Let's make this sine squared t. And that way we don't know the antiderivative right off the bat. Because we do know how to integrate sine of t, right? So we're integrating sine squared of t. Okay, so to do this one, I do all of these the same way. I always say, well, let's assume that I do know an antiderivative of sine of t. Okay, I'm going to call it big F of t. And if it's an antiderivative of sine squared t, then that means big F prime of t equals sine squared t. Okay? So I'm assuming that we know this. Assume big F of t exists such that f prime of t is sine squared t. Okay. Well then, what is, before we take an antiderivative, or sorry, before we take the actual derivative, how would we write out this integral in terms of big F? So again, we're assuming big F is an antiderivative of sine squared t. So then what is the integral from -5 to x squared of sine squared t?
Would it be f of x squared minus f of x negative, or f of -5?
Perfect. That's exactly right. We don't know what big F is. I'm just assuming it exists. Okay? And for continuous functions, by the way, they always have antiderivatives. So it's not, I mean, that's something I didn't show, but it's something that you can take for granted. Okay? So now then, I want to take a derivative, dx, of this thing. Okay? Well, once again, I've left myself no room. dx. Okay? So the thing on the left, I mean, that's what we're trying to find. So I don't need to do anything more on the left. On the right, I'm going to end up with, well, what's the derivative with respect to x of big F of x squared? There's definitely going to be a 2x involved, I agree, but it's not just 2x. what does this look like? There's a special rule that we need to use to differentiate this. So for instance, if I was just if I was differentiating, let's give a specific f, 1 plus x squared to the 3 halves, what rule would you need to differentiate this? Chain rule, right? So that's for x squared inside some other function. Well, that's exactly what we have here. We have x squared inside some other function. We don't know big F, but that's okay. We can still write big F prime. There's nothing wrong with that. And in fact, big F prime is the only thing we know about big F. Okay? So I need to use the chain rule to differentiate this. Okay, so let's do that. The derivative with respect to x of big F of x squared. I need to know what is my outside function and what is my inside function. So let's start with inside. What's my inside function? X squared. That's pretty clear. And what does that make the outside function? Yeah, just big F of x. Very good. Okay, so then I'll take a derivative with respect to x, d dx, d dx. What do I get for the derivative of x squared? 2x, very good. And the derivative of big F of x?
Little f of x.
Yeah, f prime or little f, whatever we want to call it. For right now, I'm going to write big F prime of x. Okay, so when I take this derivative, I'm going to end up with, well, the outside derivative evaluated at the inside. So that's big F prime evaluated at x squared, and then times 2x. But then again, remember, big F prime of t is sine squared of t. So that means big F prime of x squared is what? Sine squared of x squared. Yeah, very good. Sine squared of x squared. Okay, and then times, I'll write the 2x out in front. Do you need to write the 2x out in front? No, I just know that I might accidentally put it inside the sign of x if I don't do that. Okay? So that's the second fundamental theorem of calculus used on a few examples. You're not really going to see it used any differently than that, really. It's always going to be, here's some function defined by an integral, and there might be bounds. I mean, yeah, you might have more complicated bounds on the top. You might have an x on the bottom as well. You might have something with x going on in the bottom. And then you just need to worry about differentiating this as well. But that's not a big deal. We know how to take derivatives. So, but the second fundamental theorem of calculus problems don't get much more complicated than that. Okay? Are there any questions about this? So our answer for that last problem, by the way, is the derivative with respect to x of the integral from -5 to x squared sine squared t dt is equal to 2x sine squared of x squared. Pretty wild. So here's a summary of what we've been covering the last couple of days. Okay, so the first fundamental theorem of calculus says if I'm taking an integral of a continuous function on the interval a to b, and big F of x is an antiderivative of little f of x, then the integral from a to b of little f of x with respect to x is just capital F of b minus capital F of a. Okay. Fundamental theorem of calculus. Normally when someone says the fundamental theorem of calculus, they're referring to this one. The second fundamental theorem of calculus says if f of x is a continuous function on an interval I containing the point x equals a, then the derivative with respect to x of the integral from a to x of f of t dt is just equal to f of x. Okay. Any questions there? All right, then let's look at a few cool applications of the integral and the fundamental theorem of calculus. So we've already seen that anti-differentiation is really useful. For instance, when you're talking about falling objects, in physics, you always start off with a equals, when you're talking about a falling object, a equals negative g, where g is either, if you're using meters and seconds, then g is 9.8 meters per second squared. If you're using, this should be a minus. If you're using feet and seconds, then g is negative, or g is 32 feet per second squared. I have the negative there because things fall down, and I consider down to be negative. Other people don't, and they're weird. Okay? So, but starting from this, you know the v prime is equal to g, so you can find an antiderivative to find what v is. Okay? And then from there, you can find an antiderivative to find what the position has to be. This is a very simplified model. If you're interested in what about wind resistance, you can actually factor that into this equation. It becomes much more complicated, and that's something that we solve in my numerical analysis class. So plug for the future. If you want to look at even cooler stuff than this, take math, be a math major. So we always start here, though, with a falling object. A of t is negative 9.8 meters per second squared. Okay, I'm a meters per second squared guy. So we can also use integration to look at this situation of a falling object, right? We talked about it in terms of antiderivative, but integration and antiderivatives are so closely related that we can use integration a lot of the time to do the same thing that just an antiderivative does. Okay, so one thing that's going to be very important is what's called the net change theorem. So the definite integral of some f prime of x, which tells you the rate of change of big F of x, gives you the total change or the net change in f of x on the interval a to b. Okay, and I mean that's pretty clear. I mean this is just a restating of the fundamental theorem of calculus, right? The change in f from a to b is just f of b minus f of a, but that is the integral from a to b of f prime of x. Okay. So we can use that then on an example like this. A chemical flows into a storage tank at a rate of 180 plus 3 times t liters per minute, where t is the time in minutes and 0 is less than t is less than 60, less than or equal to. Find the amount of the chemical that flows into the tank during the first 20 minutes. Okay. So the amount of the chemical that flows into the tank in the first 20 minutes. So I've got some tank with, we don't know it, maybe it starts off with chemicals in it, right? Who knows? But we know that I start pumping in chemicals into here. I want to know how much of this chemical did I add in the first 20 minutes. And I know the rate at which I'm adding this chemical. Okay. So then, if I call big F of t the amount of chemical in the tank after t minutes, then what am I really trying to find? If I want to know how much did I add in the first 20 minutes, then what am I really trying to find? Not little f of t, because this is, I'm really trying to find, I want to know, maybe big F was not the best choice, but big F is something that I'm interested in. Big F is the thing that I'm trying to find the change in, right? So if I want to say how much did big F of t change between t equals 0 and t equals 20, well, what would it be? Don't overthink it. Don't even think of calculus. How much did big F change from t equals 0 to t equals 20? T changed 20, and then how much did big F change in that time? Big F of t.
180 plus 3t?
That's the change for at any, that's the instantaneous change at any time. But if I want to know how much change there was in big F between t equals 0 and t equals 20, well, let's look at big F for a second. Big F is doing something like this. I don't know. But here's 0. Here's 20. Here's where F ends at this process. Here's where F started. How do I find how much change happened there? Yeah, take the difference, right? So I want to know what is F of 20 minus F of 0. Okay. So the change in some function between two times, yeah, just take the difference of second F at the second time minus F at the first time. Okay. That doesn't require calculus at all. But now we know the rate at which big F is changing. This 180 plus 3t is big F prime, right? That's the rate of change of the chemical in the tank. Okay, so we're going to use the second fundamental theorem of calculus, or sorry, the first fundamental theorem of calculus to say, well, big F of 20 minus F of 0, or this is also that net change theorem that was on the previous slide. This is the integral from 0 to 20 of big F prime of t with respect to t. Right? I mean, that's just the, again, that net change theorem is just the first fundamental theorem of calculus. But big F prime, again, big F prime of t, we know is 180 plus 3t. So then we can just take the integral to find this problem, find the answer to this problem. We want the integral from 0 to 20 of 180 plus 3t. Okay, this is what we want. This tells us the net change in the amount of chemical in this tank. Okay. All right, so let's evaluate this. What's an antiderivative? Or we'll break this apart. This is the integral from 0 to 20 of 180 with respect to t, plus the integral from 0 to 20 of 3t with respect to t. Okay. What's the integral from 0 to 20 of 180? Or just what's an antiderivative of the number 180? Or we could think about it as I could pull 180 out in front. 180 is a constant. So the integral, 180 times the integral from 0 to 20 of just 1 dt plus 3 times the integral from 0 to 20 of t dt. So what's an antiderivative of just 1?
X.
Yes, but we're using t's here, so I'm going to write a t. So the integral of 1 with respect to t That's going to give me t plus 3 times, what's an antiderivative of t? T squared over 2. Perfect. Add 1 to that exponent, then divide by the new exponent. Very good. I'm going to evaluate this at t equals 20 and t equals 0. Well, when t equals 0, both of those terms are just 0, right? And so I really just need to know what is this when t equals 20. So when t equals 20, I'm going to get 180 times 20 plus 3 times 20 squared divided by 2. And then really, again, really minus 0. So this is, well, 0, 0, 3, 6, 3, 3,600 plus 3 times this entire guy right here? Yeah. It should be 2, yeah, because this is 3 times 10 times 20, so yeah, 600 for the second one. So 3,600 plus 600, oops, 600 gives me 4,200. And this was, what were the units on this? Does anyone remember? Well, the rate of change was given in liters per minute. So what is my answer? What are the units? This was, I wanted to find out how much change there was in this tank. Careful. So when you integrate with respect to t, that gets rid of the time unit. So this is really just liters. Yeah. Another way to think about it is this was f of 20 minus f of 0. F is just in liters, right? Okay. Any questions on that? All right. And then the second question, can we say how much of the chemical is in the tank at 20 minutes? What do we think?
I would say no, just because we don't know if there was anything in the tank before we started adding.
Exactly right. We only know how much we've added. We don't have any idea what we started with in the tank. If the tank started with 10 liters, well, then we know that we added 4,200 liters, so there's 4,210 liters if we started with 10. But we don't know how much we started with, okay? And this is what makes this a little more powerful than just starting with 180 plus 3t, knowing this is f prime of t, and then trying to find f of t. Well, that would be 180t plus 3t squared over 2 plus some constant. We don't know the constant. But with the net change, the constant doesn't matter, okay? So we just want the net change. We can just take the integral. All right. So next time we'll pick up here talking about the difference between displacement and total distance traveled. Okay, and that'll come up on, I'm not going to give you homework over Thanksgiving break, but it'll come up on a quiz next week. Okay, so thank you all for being here. If you have any questions, I have office hours today, 1 to 3, and you can also just ask me after class. Who cares? Life is short. Do what you want. So everybody have a great weekend, and I'll see everybody on Monday. Thank you.
Thanks.